All right, welcome back to, I guess, part two of this project. Learned a lot in the past week, and hopefully I can explain it to you. Because if I can explain it to somebody and not have them call me out on it, that kind of means usually that I understand it a little bit. We're going to ignore all this for now, but what I've discovered, I patched in a battery here as I told you I would, and I can just hook this up, and that works fine. There's a 5-volt regulator inside this thing, and what I've done is I've just tied in a 9-volt battery to the input side of that 5-volt regulator. So anything over maybe about 7 volts or so will be enough to power this up. This is acting a little funny because it doesn't see any kind of AC signal coming in, so it's not going to finish initializing. But that's okay because with the display fully engaged like this, let's say, I was actually able to figure out how this is multiplexed. And I'm going to show you how I did that. So over here, let me maybe zoom in a little bit. Okay, so you can see the display and this breakout over here that I did. Now there's a lot of noise in here, and I'll get to that later, but this is good enough to figure out what I was doing. So what I found out, if I ground out any of the data lines, so let's see, we'll start with this one. You can see how the elements fade. So I was able to use this method to figure out what all the different data lines were. And then for the comm lines, which I already kind of identified because I hooked up my oscilloscope and I could find out exactly what's going on. What I can do is hook up any of the data lines to the comm lines, and that completely shorts them out. And so here's comm 1 is all these elements here, and comm 2 is all these elements here, and COM 3 and COM 4. So taking all that information into account, I was able to make a little diagram. And this is basically how the LCD works out. So knowing this, I can take all of the different channels, read them into a microcontroller, and figure out what the display is showing. I don't necessarily need all these channels, but it's good to have them. So with that all figured out, my next challenge now, the battery part is solved. That's real easy. Just throw in a switch and maybe an LED to let me know that it's on battery power, and then I'll be able to unplug it and have it remember everything. In fact, let me get out the power strip here, and we'll just give this some AC power, and I'll show you what I mean. That's on. That is now on. Alright, so we're on AC power now, and you can see that the display is a little screwed up. It's looks like 188, but it's not. It's because of all this stuff over here is interfering with the display. That's really a 60. That's 60 hertz. But if I hook up the battery, you see nothing changes. But then I can turn this off, and it just goes down to 0. 0 hertz makes sense. Or actually, I guess that's supposed to be OC. It looks like 8C. I don't know. OC would make sense, but you can see 0 volts. That's supposed to be 0.00 amps, and this element here is not actually supposed to be active at all. In fact, I don't think any of this stuff up here is either. But that's, again, because of all this wiring and the capacitive coupling, and it's being messed with. I have probed at least one of these channels after removing the wire. I opened it up again, hooked it up to my oscilloscope, and I get some nice clean traces off of it, and I was able to measure some voltages. So I know what I'm actually dealing with, and by the time this mod is finished, if I finish it, this problem will go away, I hope. Now that I know what signals to look for, and what the various voltages level are, I need to kind of condition the input voltage, make something that's microcontroller friendly. So I've read a couple of things. What some people try to do is use the analog inputs of a microcontroller, like this Arduino here. That could work if you get it right, but I think I have a better way. Not necessarily a simpler way, but a better way. And that is to use a comparator. And let me just turn this light off so it's not so glary. There we go. So basically the input signal looks kind of like this. And measuring with the oscilloscope, I get 3.2 volts and 1.4 volts as sort of like the inactive state. This would be one of the COM channels. And it kind of just flicks in between those two voltages to keep the LCD in a neutral state. And then it'll go low and high to activate that that element, let's say. And I want to convert that into basically a clean pulse and eliminate the rest of that stuff. And I can do that using an op amp in a comparator configuration, and we get kind of an output like this. So when the input voltage, on this case I'm using a non-inverting setup, so the input voltage is on the positive input, and the reference voltage, which we can tweak, goes into the negative. But when the input voltage goes above the reference voltage, then the output will suddenly switch on, and then it'll turn off again when we go back below it. This has some pros and cons. I mean, you could use like a Schmidt trigger or something like that, give a little bit of hysteresis in case there's a lot of noise in here. But I'm hoping that by the time I remove all those extra jumper wires that I added, there won't be too much noise to deal with. So I'm kind of banking on this as a provisional thing. You could use maybe a dedicated comparator chip, and I'll see if I have any. I probably don't. I have a whole bin full of like miscellaneous chips and stuff. But if I don't, I do have op amps. I could always buy a comparator chip if I get to the point where I want to really make a good project out of this instead of just a learning experience. But we'll burn that bridge when we get to it. Okay, so on here, I have everything set up. And what we're showing here is channel 1, which is the green channel, which is the input off of COM 4, or pin 4, I guess you'll just say. And you can see we've got some of these weird curly tails in there. That's because of the extra wiring that I added and the extra capacitance and crosstalk that they have. Probing that without the extra wires, we don't really get that. So it's a fairly clean signal. And then what I'm going to do is, this is channel 2, which is the output of the comparator circuit that I built. And as you can see, it's got a little bit of noise in it. More than a little bit, actually. It's kind of all over the place. But I think that's going to be okay. Again, a lot of this noise should go away once I make a cleaner mod out of it. But if we show both, we get a little freaky. And you can see that the high point of the output for the comparator is equal to, or in time with, the main pulse on the COM line, which is exactly what we're looking for. Let me just put in a little cursor here. We're going to just call that 0 volts, right? That'll be our reference. Whoops. And we'll do this here. Now for TTL logic, like what the Arduino uses, we need at least 2.5 volts, I would say. Probably, no, the closer to 5 we get, the better. But as you see here, is it fair to say we get 3 volts? Not really. We get at least 2.8 volts out of that, which I think is good. And then the peaks of the noise, which maybe I can turn just a little bit. The peaks of the noise here are down well below 2 volts. So I think we'll be okay. I think the microcontroller won't get too confused. I could try adding a little bit more capacitance to the circuit. In fact, let me show you what happens if I remove this 4.7 electrolytic capacitor, 4.7 microfarad capacitor. Doink. Alright, now these little dots here on the output, again, I'm hoping most of this stuff will go away when I clean up the mod, but just in case, that's going to be a problem. And we got a lot of noise now, and we got these little, I guess you can call them false triggers that might throw a monkey wrench into the works. So I'll just put that capacitor back. And that kind of, it delays things enough that the little tiny peaks don't make it through, right? It's basically acting as a filter, like a high-pass filter. So that's not bad. Yeah, 1.6 volts. Anything below 2 volts should not trigger a logic high on a TTL input. So with this, I should be able to do digital reading of all the channels. I will need 20 op amps, 20 comparators total, but maybe I can reduce that a little bit, eliminate a couple channels because I don't think I need them all. I can definitely eliminate at least 2, I think. But we'll see what happens. And yeah, I'm looking forward to this. I think we might be able to get something that works. This part here, on the rising edge here, is a little wonky. But again, anything above, where's 2.5 volts? There's 2.5 volts. I think we'll be okay. I think that'll read as a logic 1 no matter what. And I can avoid using a whole bunch of analog inputs Let me turn off channel 2 because that's really confusing. And if we screw around with the trigger level a little bit, we can get it to offset itself. That's perfect. I'm glad I managed to get it that quickly. Let's just try to measure the period here one more time. Yeah, that could be 15.5 milliseconds, which is 64.5 hertz. Or if we just want to measure one pulse, that would be a whole frame. So there's 4 pulses per frame. But if we want one pulse, I think it's fair to say 3.8, 263 hertz, which is kind of an oddball number, but I can't really justify 264 hertz. Maybe I can. It's kind of like right on the edge there. But we have, let's say, 3 milliseconds. Not even, actually. We only have half a pulse to make that measurement, don't we? No, we have a full pulse, because the way the comparator works, if it's way outside the voltage range, then we're getting an output, which is good. So we have, let's say, 3.5, not quite 4 milliseconds to make our measurement and then check all of the other lines. So what I can do, I hope, is maybe put in an interrupt on the 4 comm lines if I can get something that has 4 external interrupts. If not, I'll just do like 1 or 2. And then input all of the other channels at once. I can input an entire 8-bit port, at least in Arduino. Any other microcontroller probably has a similar functionality. And input the whole thing, and hopefully we can get the timing right. And then we don't have to do that all the time either. Like the display refreshes a lot faster than the device actually updates its own readings. So we make a reading, we have at least like half a second, 500 milliseconds or so to decode it, write it out someplace to store it, and then go back and reset our interrupts and all that. And that's where I stand right now. So I just need to figure out, I guess I've already figured out how to condition the signal, a decent way to condition the signal, and just build up the rest of the circuit. 20, I'm going to need 10 of these things. There's got to be, I mean, for now I'm just going to breadboard it and it's going to be a right mess, but in the meantime I think we can work with this and I'll figure something out and I'll give you another update next week. So, woohoo! Full steam ahead.